Welcome back. Let's learn about planes in 3D space. Alright, so in the previous lesson, we talked about how we can represent lines within 3D space, but now what we're going to do is look at how we can represent our first type of surface in three-dimensional space, which is a plane. And if you're not familiar with what planes are, we're not talking about airplanes here, we're talking about flat surfaces within the three-dimensional coordinate system. You can think of planes as being like a sheet of paper. It's a very thin, flat 2D surface. But now, of course, unlike a piece of paper, a plane in the three-dimensional coordinate system will extend out forever within 3D space. Unless we were to apply some restrictions to it, of course. Okay, but now when we actually want to go about representing planes in 3D space, there are two things that we're going to need. And you're going to see that those two things are very similar to what we need to represent lines in 3D. Remember from the previous lesson that in order to represent a line in 3D, we needed a point on that line and a vector that is parallel to that line. And we called that vector the direction vector. And so those are the two things that we needed for a line in 3D space. And as it turns out, we need two very similar things to represent a plane in 3D space. In particular, we're going to need a point on that plane, and we are going to need a vector, but this time we want a vector that is perpendicular to the plane. All right, so that is a little bit different compared to what we needed to represent a line in 3D. For lines, we need a point on that line and a vector parallel to the line, but for a plane, we need a point in that plane and a vector that is perpendicular to that plane. And we have a special name for that perpendicular vector. We call it a normal vector. And so if we have a normal vector, or a vector perpendicular to a plane, and a point within that plane, we can represent that plane in 3D space. Okay, and visually that looks like this. We could pick any point within the plane. I'm going to pick a point right here, and we'll just say that that point is a point P1 with coordinates x1, y1, and z1. All right, just some point within that plane that has a particular x, y, and z coordinate. And then for our normal vector, it might look something like this. It does not have to extend from that point that we're using in the plane, but to keep things simple, that's where I'm going to draw it. And we represent that normal vector like this. We use the letter n and then our vector notation. And it is important to remember that that vector is perpendicular to the plane, and so it would make a right angle with the plane. And so this would be an example of a normal vector for this plane right here. And it's important to realize that for any plane in 3D space, there's not just going to be one normal vector, right? If we look at this plane on the side here, we could draw an infinite number of vectors that are perpendicular to this plane, right? I could continue to draw more and more vectors from different points on this plane and create a normal vector. There is not just going to be one specific normal vector for any plane, but notice that all of those normal vectors would be parallel to each other since they're all perpendicular to the plane, right? If they all create a right angle with the plane, then they all would need to be pointing in the same direction. They're all parallel. And so as a result, they would also be scalar multiples of each other as well. All right, and so all that to say this, there's not just one correct normal vector that we can use to represent a plane, as long as we have a vector that is perpendicular to that plane and a point within that plane, we can use those two things to represent a plane in 3D space. Okay, so that was a quick introduction on what we need to represent a plane in 3D, but how do we actually go about using a point and a normal vector to create an equation of a plane in 3D space? Well, that's what we're going to look at next. Okay, so in order to find the equation of a plane in 3D space using a point on that plane and a normal vector, or a vector perpendicular to that plane, the first thing that we have to do is define this normal vector, right? What would that normal vector be equal to? Well, we don't know. It's going to depend on the specific plane we're looking at, but in general, we'll represent it like this. We'll say that a normal vector would be equal to a vector with components of A, B, and C. All right, those are the x, y, and z components for that normal vector. What those actual components are equal to is going to depend on the plane, but this is how we will represent them generally. And so now we've defined our normal vector, vector n, But now what we want to do next to represent this plane with an equation is consider a vector within the plane, a vector that would be parallel to the plane and within it. And the way we will create that vector is by using this point that we know is in the plane, this point P1 with coordinates x1, y1, z1. Using this point and any other point within the plane, we could create a vector that lies in the plane. All right, so using point P1 with coordinates x1, y1, and z1, and any other point within that plane, which we are going to represent with just a generic point P with coordinates x, y, and z. And remember that that is in the plane. Here's the vector that we can create. We can create vector P1P, whose components we could find by subtracting the coordinates of the initial point from the terminal point, right? So we would subtract x1 from x for the x component. We would subtract y1 from y for the y component, and then z1 from z for the z component. That's how we would create a vector from these 2 points. So we'll do that here. We'll have x minus x1, y minus y1, and z minus z1. This is now a vector contained within this plane. And so just to kind of give you a visual of what we're doing here, we're using this point right here, point P1, as the initial point of this vector, and then we're just choosing some other point within this plane. You could say that it's right here, doesn't really matter, it's just a point within the plane somewhere, and we are creating a vector between those 2 points, and that vector is within the plane. Okay, that's the whole idea of this vector right here. We're just representing a vector that is in the plane we are trying to represent. But now thinking about what's going on between these 2 vectors, vector n, our normal vector, and our vector P1P, I'm just going to quickly label that here. This is vector P1P right here. Since the normal vector is perpendicular to the plane, what that then also implies is that that normal vector would be perpendicular to every vector within the plane, right? All vectors that are within this plane would be parallel to the plane. And so if the normal vector is perpendicular to the plane, then that vector must also be perpendicular to any vector within that plane, including vector P1P. So we can conclude that vector n, the normal vector, is perpendicular to vector P1P. And what do we know about perpendicular vectors? Well, if you think back to the dot product, remember that when you take the dot product of any 2 vectors and it's equal to 0, that means that those 2 vectors are perpendicular. So if we know for a fact that this normal vector to the plane and this other vector within the plane are perpendicular, then we can conclude that the dot product of those 2 vectors should be equal to 0. So we can conclude here that the normal vector, vector n, dot vector P1P will be equal to 0. And so if we write this out, if we perform the dot product between these 2 vectors, that's going to give us an equation that will represent this plane. All right, the dot product of these 2 vectors is going to involve the components of the normal vector and the coordinates from the point within our plane. Both of the things I said we needed in order to represent a plane in 3D space. Okay, so here's what happens if we take this dot product. Remember that the dot product of 2 vectors is equal to the sum of the product of corresponding components. And I know that that sounds fancy, but really all it means is that we multiply the x components together, add that to multiplying the y components together, and then add that to multiplying the z components together. And so if we do that, it'll look like this. We'll have a times x minus x1. So let's write that down. We'll have a times x minus x1, and then we're going to add that to multiplying the y components together. So we'll have b times y minus y1. So I'll write b times y minus y1, and then we'll add that to multiplying the z components together. So we'll have c times z minus z1. And so I'll write c times z minus z1, and this dot product calculation right here that we just wrote down needs to be equal to 0, so we will write equal to 0. And so what we have right here is an equation that we call the standard equation of a plane in 3D space. This is a very important equation for you to remember. This equation right here is how you can take a normal vector for a plane with components a, b, and c, and a point within that plane with coordinates x1, y1, and z1 and create an equation of that plane in 3D space. Okay, now this is just the standard form, but there is actually another form of the equation of a plane that we can find by simplifying this equation right here. If we distribute A through this quantity, B through this quantity, and C through this quantity, we can create a slightly different equation. And so let me show you what I mean. If we work with this equation up here and rewrite it after distributing A through this quantity, B through this quantity, and C through this quantity, we will have A times x minus A times x1, then we will have plus B times y minus B times y1, and then plus C times z minus C times z1, and that is equal to 0. Okay, and now what's important to realize about this equation is that x, y, and z are our variables, right? Those values represent the coordinates of any other point within the plane, the points that together would make up this entire plane. But x1, y1, and z1 represent the specific coordinates of one particular point that we are using to represent that plane. Okay, that can be a little bit confusing at first, but just remember that x1, y1, and z1 are the specific coordinates of a particular point that you've been given, but x, y, and z represent any other point that could be on that plane. And so x, y, and z are our variables, while x1, y1, and z1 are just constant values, right? They represent specific coordinates. Now, a, b, and c are also constant values. They're just the components of the normal vector. And so these three terms right here, where we are multiplying the components of the normal vector by the specific coordinates of the point in the plane, those three terms represent constant values, right? They do not involve a variable. So negative a times x1, negative b times y1, and negative c times z1 are all constant values. And so what we can do is add those values to both sides of this equation so that the variable terms and the constant terms are separated. And if we do that, that'll look like this. We'll have a times x plus b times y plus c times z, and that will be equal to those other three terms that will now be positive because we're adding them to both sides of the equation to cancel out with their negative versions on this side. So we have a times x1 plus b times y1, and then plus c times z1. And then what we can do to simplify further is, since these three values are constant values, right, we have already determined that when you actually write out the equation of a plane, those three constant values will be combined together to create one constant value. And so that's what we're going to do in this case. We are going to group those together to be one constant value that we will represent with d. All right, and then if we fill in the rest of the equation, we'll have a times x plus b times y plus c times z. And this right here is what we call the general form of the equation of a plane. Okay, so this is the standard form. This is the equation that you will use when setting up an equation of a plane. But then this is the general form, which is the most common type of equation that you will see to represent a plane. And you'll see that as we progress throughout Calculus 3, and even within this video and the examples video for this topic, planes will generally look like this equation right here, where you have some constant times x plus some constant times y plus some constant times z equal to some constant value. All right, but these two equations right here are the two different forms of the equation of a plane in 3D space that you need to know. And so to summarize, if you want to represent planes in 3D space, you're going to need to know two things. You need to know a specific point in the plane, P1, with coordinates x1, y1, z1, and you need to know a normal vector, or a vector perpendicular to that plane, with components a, b, and c, and then using that vector and that point, you can set up the standard form of an equation of a plane, which looks like this: a times x minus x1 plus b times y minus y1 plus c times z minus z1, which is equal to 0, and then simplifying this equation will give you the general form of the equation of a plane, which looks like this. You have a times x plus b times y plus c times z equal to some constant value d. Okay, and so now that you've been introduced to how we represent planes in 3D space, or the equations that we will use to represent them, as well as where those equations come from, we are ready to look at some example problems of finding equations of planes in 3D space. Okay, so here's our first example. We want to find an equation of a plane with a point 2, 5, -1 and is perpendicular to the vector n, which is the position vector of the point 1, 2, 3. All right, so remember, if you want to find an equation of a plane, you need two things. You need a point in that plane and a vector that it's perpendicular to, or a normal vector, and we have both of those things given to us in this example. We have a point within the plane and a vector perpendicular to it, which is this normal vector right here. Okay, and you can see that I have our standard form of the equation of a plane right here for us to reference. And so all we have to do in this problem is fill in this equation with the appropriate values from the coordinates of the point and the components of the normal vector. All right, now the first thing that I recommend that you do is write down what the components of the normal vector are. And what I mean by that is we should write down what A, B, and C are, the X, Y, and Z components of this vector. So we know that A is equal to 1, B is equal to 2, and C is equal to 3, right? A is the X component, B is the Y component, and C is the Z component. I think it's helpful to write those three values down explicitly so that you're less likely to make a mistake when setting up this equation. Because one of the worst things that you could possibly do here is put the wrong numbers in the wrong places in this equation. All right, you don't want to plug in the coordinates of the point in for A, B, and C, or plug in the components of the normal vector in for x1, y1, and z1. You want to make sure that you put those in the right spots in this equation. And so I think writing out what A, B, and C are equal to can kind of help you avoid making those mistakes. Okay, but now with that, let's actually start writing out this equation. We know that A is equal to 1, so we'll have 1 times x minus x1. I'll start by writing that. We'll have 1 times x minus x1, which is the x coordinate from our point, and that's 2. So we'll have x minus 2, and then we will add that to b times y minus y1. So we will have 2 times y minus y1, which is the y coordinate of our point, and that's 5. So we will subtract 5, and then we will add that to c, which is 3. So we will have 3 times z minus z1, which is the z coordinate from our point, and that's -1. So we are subtracting -1. And then that's equal to 0. All right, and so now what we want to do is simplify this equation. This is the equation of the plane in this example in standard form, but typically we don't give that as an answer. We like to simplify the equation down into the general form of the equation of a plane, which was that second equation that we found earlier. All right, that's this form of the equation of a plane right here. When we're done simplifying this, we should have a times x plus b times y plus c times z equal to some constant value. So let's work on that. 1 times x minus 2 is just going to give us x minus 2. Then we'll have plus 2 times y minus 5. So we will have 2y and then minus 10. And then we have plus 3z minus -1. Z minus -1 is the same as z plus 1. So I'm just going to rewrite this to be z plus 1. And then 3 times z is 3z, and 3 times 1 is 3. So we have plus 3z plus 3, and that's equal to 0. And now what we want to do is separate our variable terms from our constants. All right, we want to move all of the constant values over to the other side of the equation and just be left with the x term, the y term, and the z term. Okay, so we're going to be taking -2, -10, and +3 and moving them over to the other side of the equation by performing the opposite operation, right? We're going to be adding 2 to both sides, adding 10 to both sides, and subtracting 3 from both sides. And so if we do that, we will be left with x plus 2y plus 3z is equal to 2 plus 10 minus 3. All right, now if we simplify this, 2 plus 10 is 12, minus 3 is 9, and so this will just become 9. All right, and this right here, x plus 2y plus 3z equal to 9, is an equation of the plane in this example that contains this point and is perpendicular to this normal vector. All right, and if you compare this equation to the general form of an equation of a plane, you can see that it matches up. We have a times x, which in this case is just 1 times x, so we just have x, plus b times y, in this case b was 2, so we have 2 times y, and then we have plus c times z, and c was 3, so we have 3z, and then we set it equal to some constant value, which in this case is 9. All right, this -2, -10, and +3, those were those constant terms that we were looking at earlier of a times x1 and b times y1 and c times z1, right? Those were those terms that I was telling you were constant values that we would add over to the other side of the equation and would combine to be one constant value. That is exactly what happened here after simplifying this standard form of an equation of this plane. Okay, and so that's how we find an equation of a plane in 3D space, at least when we're given a point and a vector that it's perpendicular to. But let's take a look at a slightly different example of finding the equation of a plane. All right, here's our second example. We want to find an equation of a plane with a point 6, -2, 3, and is parallel to 3x minus y plus 2z equal to 5. Okay, so unlike the previous example, where we were given a point on the plane and a vector perpendicular to that plane, this time we are given a point on the plane and then another plane, right? This is the equation of a plane. It's an equation of a plane in general form. We have some value times x plus another value times y. In this case, that would be -1. So we have 3x minus y. But then we have plus another value times z equal to some other constant value. This is an equation of a plane. All right, and so if we want to find a plane that contains this point and is parallel to another plane, how do we find that plane? Well, let's think about it visually. Let's say that our plane looks something like this. This is the plane that we were trying to find an equation for. If we were going to represent that plane traditionally, we would use a point in that plane and then a vector perpendicular to it, right? A normal vector. But if we know a plane that's parallel to that plane, maybe that plane looks something like this. This plane would also be represented with a point and a normal vector. All right. And so if you think about this, if we're trying to find a plane that we know is parallel to another plane, and both of those planes would be represented using a normal vector, a vector that is perpendicular to those planes, then it's safe to say that those two normal vectors that are perpendicular to their respective planes would also be perpendicular to the other plane, right? If these two planes are parallel, and these two normal vectors are perpendicular to each of those planes, then those two normal vectors must also be perpendicular to the other planes. Or another way to think about it is that those two normal vectors are parallel. They are pointing in the same direction. So this normal vector is perpendicular to this plane, but it's also perpendicular to this plane. Just like this normal vector is perpendicular to this plane, and therefore is also perpendicular to this plane, because those planes are parallel. And so all of that to say this, two parallel planes will share a normal vector. That normal vector will be the same. Or more accurately, they might not be exactly the same, but they are parallel and therefore are scalar multiples of each other at the very least. But regardless, what we can do here to find the equation of this plane is just use the normal vector from the plane parallel to it. And if you think about the general form of the equation of a plane, we have a times x plus b times y plus c times z equal to some constant d. We can very quickly find the normal vector from this plane using those values of a, b, and c, right? The normal vector to a plane has components of a, b, and c. So if we look at the coefficients of x, y, and z in this plane equation, we can find the normal vector for the plane that's parallel to the plane we're trying to find an equation for, and then we can use that normal vector and this point right here to represent that plane. Okay, so it all comes back to what we originally said. We still need a point and a vector perpendicular to our plane to represent it, but sometimes the way that we get that perpendicular vector, or that normal vector, is a little bit different. In this case, we are getting it from another plane, a plane that is parallel to the plane we want to find. Okay, so let's find the normal vector for this plane here. The coefficient of x is 3, so a is equal to 3. Let's write that down. A is equal to 3. Then the coefficient of y is b. In this case, we have negative y, so the coefficient is -1. so b is equal to -1. And then for c, that's the coefficient of z. So if we look at this term here, we have 2z, and so the coefficient of z is 2, which means that c is equal to 2. All right, so the normal vector for that plane would be equal to the vector with components of 3, -1, and 2. And then using that normal vector and this point on the plane that we want to find an equation for, we can find that equation. All right, we're going to set up that equation in standard form and then simplify it. And so we're going to have a times x minus x1. So we will have 3 times x minus x1, or the x coordinate from our point, which is 6. So we'll have 6. And then we're adding that to b times y minus y1. And b is -1. So we will have -1 times y minus y1, the y coordinate from our point, which is -2. So we're subtracting -2. And then we're adding that to c times z minus z1. C is equal to 2. So we have 2 times z minus z1, the z coordinate from our point, which is 3. So we have z minus 3, and then that's equal to 0. All right, now that's our equation in standard form, but now what we want to do is simplify it into the general form. So we're going to distribute 3, -1, and 2 through their respective quantities here. So we'll have 3 times x, which is 3x, and then 3 times -6, which is -18. And then we have -1 times y, that will be -y. And then before we multiply -1 by -2 here, do notice that we have y minus -2. That's the same as y plus 2. So I'm just going to erase those two negative signs and write plus. And so now we've already multiplied -1 by y right here, and then -1 times 2 is -2. All right, then we will add that to 2 times z, which is 2z, and then we have 2 times -3, which is -6, and that will be equal to 0. All right, and so now we're almost done. Now all we have to do is move all of the constant terms, or the constant values, over to the other side of the equation. And so that would be -18, -2, and -6. We're going to add 18, 2, and 6 to both sides of the equation, and that will give us this. We'll have 3x minus y plus 2z is equal to 18 plus 2 plus 6, and 18 plus 2 is 20, plus 6 is 26. So I'm just going to erase this and write 26. And that right there is an equation of a plane with a point of 6 and -2, 3 contained within it, and is parallel to this other plane that had a normal vector with components 3, -1, and 2. Okay, and so that's how you can find that equation for that plane. The big takeaway from this example is that if two planes are parallel, then you can use the same normal vector in the equation for those two planes. All right, since the two planes are parallel, their normal vectors are parallel as well, and so they will share that normal vector. Okay, let's take a look at a slightly different example. Hey there, real quick, before we get to the next part of this lesson, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. Okay, so next up we want to find an equation of a plane containing the following 3 points, and we have these 3 points right here, 2, 1, 1, 0, 4, 1, and -2, 1, 4. And this is a little bit of a weird problem, right? We just got done talking about how in order to find the equation of a plane, you need a point on that plane as well as a normal vector, or a vector perpendicular to that plane. But we don't really have those two things, do we? We have 3 points on the plane, which is 2 more than we need, and we don't have a normal vector. And so this seems like a pretty impossible task at first, but believe it or not, this is actually possible. And so let's think about what's going on here. If I draw a quick sketch of our plane here, let's say it looks something like that, and we know 3 points within that plane. That could be a point here, here, and here. How can we use those 3 points to represent this plane? Or in other words, how do we use these 3 points to find a normal vector, right? Because that's really what we need here. In order to find the equation of a plane, we need a point on that plane, and we have 3 of them. We have more than enough in that category, but we need a perpendicular vector. And so how do we find that from just these 3 points? Well, what we can do is create 2 vectors using these 3 points. In particular, we will create 2 vectors from the same initial point. So that might look like this. We'll have a vector here and then a vector here. And then once we have those 2 vectors, we can do something with them to find a vector that would be perpendicular to this plane, right? If you think about it, since these points are in this plane and we're creating vectors using those points, then those vectors would also be within this plane. And so any normal vector or any vector perpendicular to the plane would also be perpendicular to these vectors. And so how do we find a vector that is perpendicular to 2 other vectors, right? If you think back to earlier in Calculus 3, how did we find a vector that was perpendicular to 2 other vectors? Well, we used the cross product, right? The cross product of 2 vectors gives you a 3rd vector that is perpendicular to both of those 2 vectors involved in that cross product. All right, so that's what we have to do here. We have to use these 3 points that are contained within this plane to create 2 vectors, take the cross product of those 2 vectors, and that will give us a normal vector perpendicular to the plane that we can then use to set up the equation of this plane. And so let's get started here. Let's work on finding 2 vectors within this plane. And the way that I'm going to do it is to first label each of these points. I'm going to say that this is point A, this is point B, and this is point C. And I'm going to let point A be the initial point of both vectors. And so this might be point B and this might be point C, meaning that we're going to create 2 vectors, vector AB and vector AC. So let's do that. We'll have vector AB. We want to find that. And we want to find vector AC. All right, we're going to need both of those vectors in order to find this normal vector. Now to find those 2 vectors, we just have to write them out in component form by subtracting the coordinates of the initial point, point A, from the coordinates of the terminal point for each of those vectors. All right, so for vector AB, we will have 0 minus 2 for the x component. That will be negative 2. And then for the y component, we'll have 4 minus 1, which is 3. And then for the z component, we'll have 1 minus 1, which is 0. And now for vector AC, we will subtract the coordinates of A from the coordinates of C. So for the x component, we will have negative 2 minus 2, which is negative 4. For the y component, we will have 1 minus 1, which is 0. And then for the z component, we'll have 4 minus 1, which is 3. All right, and so now we have 2 vectors that are contained within this plane. They are parallel to that plane. And so what we're going to do is take the cross product of these 2 vectors, and that will give us the normal vector. Okay, and so let's set up this cross product. Just to make things easier to work with, I'm going to say that vector AB is vector B, and then vector AC is vector C. So we're going to take the cross product of vector B and vector C, and the way we do that is by setting up a 3x3 matrix that we then take the determinant of. All right, if you're not familiar with this process, be sure to check out my lesson on the cross product. The first row will have the standard unit vectors I, J, and K, and then the second row will be the components of vector B, or vector AB, and then the third row will be the components of vector C, or vector AC. So we're going to have negative 2, 3, 0 in the second row. So I'll write negative 2, 3, 0, and then in the third row we will have negative 4, 0, 3. So I'll write negative 4, 0, 3. Okay, and so now let's perform this cross product. We start by looking at vector I in that first row, and we cross out the row and the column that it's in, and calculate a 2x2 determinant using the remaining 4 values. So I have 3 times 3, which is 9, minus 0 times 0, which is 0. So we have 9 minus 0 times I, and then we will subtract the second term, which we get by looking at J. We'll cross out this row and this column, and use these remaining 4 values to calculate a 2x2 determinant. We'll have negative 2 times 3, which is negative 6, minus 0 times negative 4, which is 0. So we'll have negative 6 minus 0 times J, and then we're adding the last term involving K, right? We're going to look at K for this last one. We're going to cross out that row and this column and use these 4 values to calculate a 2x2 determinant. We'll have negative 2 times 0 minus 3 times negative 4, and so that will be 0 minus negative 12. And so we have 0 minus negative 12 times k. All right, now if we simplify, 9 minus 0 is 9, so this is equal to 9i, and then we're subtracting negative 6 minus 0 times j, so this is negative 6j, but then we're subtracting it, so it becomes plus 6j. And then finally we have 0 minus negative 12, which will become 0 plus 12, and so we will have plus 12k. All right, and so now we have the vector that is perpendicular to both of these vectors, which will also be perpendicular to this plane. All right, and so this vector right here is our normal vector. The x component of 9 is our value of a, the y component of 6 is our value of b, and the z component of 12 is our value of c. So let's set up an equation of this plane using this normal vector that we just found and a point in the plane, which could be any of these 3 points. We can create an equation of that plane, and I'm going to choose to use point A. You could pick any of these other 2 points if you wanted to. It doesn't matter what point you choose because they're all within the plane. You just need a point in the plane to set up the equation of it. And so we're going to have this value of A, or the x component of the normal vector, of 9 times x minus x1, which is the x component of our point, and that's 2. And then we'll have plus the y component of the normal vector, which is 6, times y minus y1, which is the y coordinate of our point, which is 1. And then we'll add that to the z component of the normal vector, which is 12, and that will be multiplied by z minus z1, or the z coordinate from our point, which is 1. And so we have z minus 1, and that's equal to 0. All right, now simplifying, we'll have 9x minus 18 plus 6y minus 6 plus 12z minus 12, and that's equal to 0. I just distributed 9 through this quantity, 6 through this quantity, and 12 through this quantity. Now what we have to do to simplify is move all of the constant terms over to the other side of the equation. So we're going to add 18, 6, and 12 to both sides. And so if we do that, we will have 9x plus 6y plus 12z is equal to 12 plus 6 plus 18. And 12 plus 6 is 18, plus another 18 is 36. So we have 36. Okay? And so that would be the equation of the plane that passes through these 3 points. And if you wanted to, you could simplify this equation further. Notice that these 3 terms and 36 are all divisible by 3. And so if you did that, you would get the simpler form of 3x plus 2y plus 4z equal to 12. That would also be an acceptable answer. If you like to reduce your equations or simplify them, you could do that as well. But with that, that is it for this example. But before we close out this lesson, I do want to show you one more thing, which is how we can quickly sketch planes in the 3D coordinate system. All right, so now we're going to look at how we sketch planes in 3D space. And it's actually a fairly simple process. There's only 2 steps. The first step is to find and label any x, y, or z intercepts. In other words, you want to find the points where the plane cuts through the x, y, and z axes. And then once you've found those intercepts, you connect them to create your plane, and if necessary, extend the plane a little bit so that you can see what it looks like. And I'll show you what I mean by that when we get there. For now, let's just focus on a quick example here of sketching a plane in 3D space. For our first example, we want to sketch this plane right here, 3x plus 2y plus 4z equals 12. And the way we go about this is to find any x, y, or z intercepts. That's step 1. And the way we do that is by setting the other variables equal to 0, right? Because when the plane cuts through the x-axis, the z-axis, or the y-axis, those 3 points are only going to have one non-zero coordinate. Okay, a point along the z-axis has an x-coordinate and y-coordinate of 0. A point along the x-axis has a z and y-coordinate of 0. And a point along the y-axis has a z and x-coordinate of 0. And so if we want to find the x-intercept, or where the plane cuts through the x-axis, we just have to set y and z equal to 0 in this equation and solve for x. We want to know what x is when the other 2 coordinates are 0. And that's pretty simple to solve, because if we set y and z equal to 0, notice that those 2 terms will just be eliminated from the equation. Anything times 0 is 0, so 2 times 0 is 0, and 4 times 0 is 0. So these 2 terms would be eliminated, and we would just be left with 3x equal to 12. And so then to solve for x, we divide both sides by 3, and we find that x is equal to 4. 12 divided by 3 is 4, and so x equals 4 is the value of x where the plane cuts through the x-axis. All right, and so if this is x equals 1, 2, 3, and 4, that would be this point right here. That is the point 4, 0, 0. All right, so we found and labeled the x-intercept. Now let's find the y and z-intercepts. To find the y-intercept, we'll set x and z equal to 0, so we can solve for y. Doing that will leave us with 2y equal to 12, right? If x and z are 0, these two terms are just going to be eliminated. They become 0, and so we have 2y equal to 12. Divide both sides by 2, and you will find that y is equal to 6. So the plane cuts through the y-axis at the value of y equals 6. So if this is y equals 1, 2, 3, 4, 5, 6, then this point right here, the point of 0, 6, 0, right? The y-coordinate is 6, but x and z are 0. That point is where the plane will cut through the y-axis. That is the y-intercept. But now for the z-intercept, we need to set x and y equal to 0 in this equation. Doing so will eliminate these two terms. They will just both become 0, and we'll be left with 4z equal to 12. Right? So 4z equals 12. And then solving for z by dividing both sides by 4 will give us that z is equal to 3. And so this plane cuts through the z-axis at the value of z equals 3. So if this is z equals 1, 2, and 3, this point right here of 0, 0, 3 is where the plane cuts through the z-axis. All right, so now we have found and labeled all three of the x, y, and z-intercepts. This plane had all three of those. Not every plane will have an x, y, and z intercept. Some of them only have 2, some only have 1, and we'll talk about that in a little bit. But this one had all three, and we found and labeled them. Now what we have to do to sketch this plane is connect those points, or connect those intercepts, and then extend the plane if necessary, which we won't have to in this case. We only really need to extend the plane or make it look nicer when we don't have all three intercepts. Okay, but if we connect these 3 points, we'll end up with a plane that looks like that. I know it just looks like a triangle, but if you can imagine, this plane would extend forever in this direction, and this direction. We're just showing where it cuts into each of the axes of the 3D coordinate system. But that is really all we can do to sketch this plane by hand. This is a good enough sketch to understand where that plane is in the 3D coordinate system. And so we're good. This is the sketch of this plane in 3D space. When you have a nice equation of a plane that has all three terms of x, y, and z, all you have to do to sketch that plane quickly is find those x, y, and z intercepts and connect the points. And the quickest way to go about finding those intercepts, by the way, I actually talked you through the process of setting these variables equal to 0 and then solving for each of them individually. But the quickest way to go about it, or kind of the shortcut method, or the method that doesn't really involve a whole lot of work, is just to divide the coefficient of each of those terms into the constant on the other side of the equation, and whatever you get is the intercept for that variable. So for example, for 3x, the x-intercept will be whatever 12 divided by 3 is, which was 4. The y-intercept is 12 divided by 2, which was 6. And the z-intercept is 12 divided by 4, which is 3. And so that would be a really quick way to find those values, plot them in the 3D coordinate system, connect them, and create the sketch of your plane. Okay, and so that's how you sketch a plane when you have all three of the variables x, y, and z in the equation. But what if one of them is missing? Well, if you're only missing one of them, if you're missing x, y, or z, the plane that you want to sketch is going to be parallel to the respective axis. All right, so if the x variable is missing, that plane will be parallel to the x-axis. If y is missing, that plane will be parallel to the y-axis. And if z is missing, that plane will be parallel to the z-axis. All right, so for example, here I have 3 different planes that we can sketch quickly. For this first one, we have 3x plus 2y equals 12. There is no z term, right? So z is missing. That means that this plane will be parallel to the z-axis. And so if we quickly plot the intercepts, notice that we basically have the same equation that we were working with before, but I just removed the z term in this one, the y term in this one, and the x term in this one. So the intercepts are going to be the same. For the x-intercept, we have 12 divided by 3, which is 4. So I'm just going to redraw this. 1, 2, 3, 4. That will be the x-intercept. And then the y-intercept will be 12 divided by 2, which is 6. So 1, 2, 3, 4, 5, 6. Right here will be the y-intercept. And let me just quickly label those points. This is 4, 0, 0, and this is 0, 6, 0. And so those are the only two intercepts for this plane, but this plane will be parallel to the z-axis since z is missing here. And so this is where that other step in the sketching process comes into play of extending your plane. Because what we're going to do here is connect these 2 points, but then we don't really have a plane, right? So what we do here is we extend it so that we can see the plane. And I'm just going to extend it in the upwards z direction. All right, this plane is going to be parallel to the z-axis. It's not going to ever cut through it. So what we can do is draw a line parallel to that line we just drew somewhere up here. I'm going to draw it right here, and then you just connect those lines, and there's your plane. Okay, and then you could shade that in if you wanted to. I'm not going to go through that here because I'm going to be drawing 2 more planes yet, and I don't want to make a mess out of this. But now if we move on to this second equation here of a plane, notice that the y term is missing. We have 3x plus 4z equal to 12. And so we're not going to have a y-intercept. This plane will be parallel to the y-axis. So the x-intercept will still be 4, right? 12 divided by 3 is 4. And then the z-axis will be 12 divided by 4, which is 3. So we're looking at 1, 2, 3 right here. This point is the z-intercept. And so for this plane, we're going to connect these 2 points. That will look something like this. And then we want to extend that plane by drawing lines parallel to the axis that the plane is parallel to, right? So in this case, we are parallel to the y-axis. So I'll draw some lines parallel to that and then connect them, and we have our plane. Okay, and then finally, let's look at this last plane here. In this equation, we don't have our x term, right? We just have 2y plus 4z. And so since the x term is missing, this plane will be parallel to the x-axis. It's going to have a y and z intercept. The y-intercept is 12 divided by 2, which is 6. So that's this point right here that we already have plotted. And then the z-intercept, once again, is 3, because we'll take 12 divided by 4 and get 3. And I forgot to label that point. Let me write that real quick. This is 0, 0, 3. Okay, but now, for this plane, we are going to be connecting the y and z intercepts, and so that will look like this. And then we want to extend this plane using lines that are parallel to the axis that this plane is parallel to. And this plane is parallel to the x-axis, since it doesn't have an x term. And so I'll draw some lines parallel to the x-axis, and that will be the extension of our plane. And so that would represent our plane in the 3D coordinate system. Okay, and once again, if you drew these planes on different coordinate systems, you could then shade them in and they would look pretty nice. But I drew them all in the same coordinate system here to save some space. But that's how you would go about sketching these planes. Once again, this plane was parallel to the z-axis. The second plane was parallel to the y-axis. And that third plane was parallel to the x-axis. It's all dependent on what variable is missing from those plane equations. Okay, so that's how we sketch a plane when one of those 3 variables are missing. But now what do we do if 2 of them are missing? Right, what do we do if our plane equation is just x, y, or z? Well, if you just have an equation of x equals some value, or y equals some value, or z equals some value, that plane will be parallel to the plane in the 3D coordinate system involving those missing variables. All right, and so let me show you what I mean. Here I have 3 examples of 3 different planes. These are the simplest types of planes that you could work with. We have x equals 4, y equals 6, and z equals 3. For this first one of x equals 4, we're missing y and z, so that means that this plane will be parallel to the yz plane. All right, and so if we were to sketch that, we're only going to have an x-intercept at x equals 4. So we'll have 1, 2, 3, 4. This is x equals 4 right here. Our plane is going to cut through that point. And so what we do to draw that plane, since we know it's parallel to the yz plane, it's going to be parallel to both the y and z axis. So we can sketch the plane by drawing lines parallel to the y and z axis. And then just connect those lines and create our plane. All right, and you could shade this in, and that would be the plane x equals 4. It's the plane that cuts through the x-axis at the value of 4. All right, so that would be the point 4, 0, 0. Now for y equals 6, that doesn't involve x or z, so that plane will be parallel to the xz plane. And so if we were to sketch this plane, we're going to be cutting through the value of y equals 6 along the y-axis. So we have 1, 2, 3, 4, 5, 6 right here. That is the point 0, 6, 0. Our plane cuts through that point and is parallel to the xz plane, which means it's parallel to both the x and z axes. So to sketch that plane, we will draw lines from that intercept that are parallel to the x-axis and z-axis, and then connect those lines. Okay, that's the simplest way to go about sketching that plane. And then finally, we have z equals 3. This equation does not involve x or y, which means that it will be parallel to the xy plane. And so if we have a z-intercept of z equals 3, then that plane will look like this. We're looking at z equals 3 right here. That's the z-intercept. We have 0, 0, 3 for that point. And to sketch this plane, we will draw lines from that intercept that are parallel to the x and y axes. All right, if this plane is parallel to the xy plane, then it's going to be parallel to the x and y axes. So I'll draw a line parallel to the x-axis and a line parallel to the y-axis, and then draw 2 more to create a plane. Okay, and so that would be the sketch of z equals 3. Okay, and once again, you could then shade each of these planes in if you wanted to. It might look a little bit messy unless you separate them into their own separate coordinate systems. But with that, that is how you sketch planes in 3D space. And that is everything that I wanted to cover about planes in this lesson video. So if you want to see some more examples of finding equations of planes and sketching planes, feel free to check out my examples video that I'll have here on the screen for you to click on. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.